Two trains are racing toward each other on a stretch of track outside Wuhan. They are not supposed to touch. They are barely supposed to pass each other, doors sealed, cabins pressurized, engineers watching from a control room miles away. Their combined closing speed hits 896 kilometers per hour, faster than a commercial jetliner at cruising. Altitude, generated entirely by two vehicles running on steel wheels, on steel rails with no wings and no runway. One of those trains, on its own, had already touched 453 kilometers per hour minutes earlier. That number matters, because it is faster than any wheel on-rail train has ever gone in revenue track testing anywhere in the history of railways. And the strangest part of this story isn't the speed itself. It's that the people who built this train weren't trying to break a record. They were trying to solve a much smaller, much stranger problem, and the record broke almost as a side effect. This is the story of the CR450, and why a train that was never designed to chase headlines ended up rewriting what a train is allowed to do. To understand how seriously this needs to be taken, you have to start with who's actually behind it. This isn't a startup with a flashy rendering and no track record. The CR450 is being developed by the China State Railway Group, the state-owned operator running the largest high-speed rail network on Earth, in partnership with the China Railway Rolling Stock Corporation, or CRRC, the manufacturing giant that builds the vast majority of China's existing bullet trains. The prototypes themselves, two of them, designated CR450AF and CR450BF, were unveiled at a press conference at the China Academy of Railway Sciences in Beijing at the end of December 2024, following roughly 5 years of design and engineering work that began in 2021. This is a government-backed, multi-year, heavily instrumented engineering program, not a viral stunt. Here's the everyday version of what this train is actually up against, because the number 453 kilometers per hour doesn't mean much until you compare it to something your body already understands. Imagine driving a car at highway speed, around 100 kilometers per hour, with your hand out the window. Now imagine that same wind force, but more than 4 times stronger, hammering against a vehicle the length of several football fields, stacked end to end. At those speeds, air isn't just resistance anymore. It behaves almost like a fluid pressing back against the train's nose with enough force to visibly slow it down and shake its structure if the shape is wrong. To put the scale in a second way, the CR450 covers the length of roughly 3 American football fields in a single second. That's not a train picking up speed. That's a train outrunning the very air it's pushing through. So why build something this fast in the first place? Not for the record. The actual engineering brief was almost mundane by comparison. China's existing fleet of CR400 Fuxing trains, the ones currently carrying passengers across the country, top out at 350 kilometers per hour in commercial service. That's already extraordinarily fast by global standards. Faster than Japan's Shinkansen, faster than France's TGV in daily operation. But China's rail planners wanted more headroom, both for raw speed and, just as importantly, for smoother, quieter, more energy-efficient travel at the speeds trains already run. The CR450 project set out to push the operational ceiling to 400 kilometers per hour in regular service, a 50 kilometer per hour jump on a network that already moves billions of passenger trips a year. The 453 kilometers per hour reached in testing wasn't the goal. It was the safety margin engineers built in above that operational target to prove the system could handle more than what passengers would ever actually experience day to day. Now here's the part that connects everything else in this story. None of that extra speed was free. Every kilometer per hour above 350 comes at a steep physical cost, because aerodynamic drag doesn't increase in a straight line as speed goes up. It increases with the square of velocity. Push a train's speed up by 15%, and the air resistance fighting against it doesn't rise by 15%. It rises by something closer to 30%. At 450 kilometers per hour, engineers were fighting a wall of resisting air that grows dramatically faster than the speed itself, which meant the entire train had to be rethought from the outside in, not just given a more powerful motor. That rethink starts with the nose. On the existing CR400 trains, the streamlined front section measures about 12.5 meters long. On the CR450, that nose was stretched to 15 meters, a change that looks modest on paper, but reshapes how air peels away from the train's leading edge at extreme speed, reducing the turbulent drag that builds up behind a blunter shape. Engineers also enclosed the bogies, the wheel assemblies underneath each car, behind smooth panels, and added lower skirting along the train's flanks, closing off the gaps and mechanical clutter that used to catch air and create resistance. The overall design philosophy borrowed openly from high-performance automotive engineering, treating the entire train less like a string of connected boxes and more like one continuous sculpted form. The train's height was trimmed by about 20 centimeters. Its total weight came down by roughly 50 tons across the full train set, achieved through new lightweight composite materials and aluminum alloys in the car bodies. Combined, these changes cut aerodynamic drag by 22% compared to the previous generation. That single number, a 22% cut in drag, deserves a second comparison because on its own it can slide past you without registering. Picture cycling into a headwind so strong it takes real effort just to hold your speed steady. Now imagine someone reshapes the wind itself so more than a fifth of that resistance simply disappears, while you're pedaling exactly as hard as before. That's roughly the scale of what CRRC's engineers accomplished. Not by making the train stronger, but by making the air fight it less. Reducing drag solved one problem. It didn't solve the harder one, which was getting all that extra speed under control again just as quickly, on tracks shared with passenger stations, curves, and other trains running at different speeds. Now this is where the recap is worth pausing for, because a lot has piled up fast. Real institutions, a real 5-year engineering program, a nose reshaped for airflow, tons of weight stripped from the frame, and drag cut by nearly a quarter. All of that got the CR450 up to speed. The next part of the story is about stopping it, and it turns out that's where the real engineering achievement was hiding the whole time. At 400 kilometers per hour, a train carries dramatically more kinetic energy than the same train at 350. Again, because that energy scales with the square velocity, not in a straight line. In practical terms, that means a faster train needs disproportionately more margins of a slower one, or it needs an entirely smarter way of shedding that energy. China, Railway Rolling Stock Corporation's engineers set themselves a specific, almost stubborn target. The CR450, braking from 400 kilometers per hour, had to stop within the same 6,500 meter emergency braking distance that the older CR400 trains use when braking from 350. Not a longer distance to accommodate the higher speed. The exact same distance, despite carrying meaningfully more energy to dissipate. They hit that target using what China State Railway Group has described as high-performance braking technology paired with permanent magnet traction motors, a combination that allows the braking system to convert far more of the train's kinetic energy into controlled electrical resistance, rather than relying purely on mechanical friction, the way older systems do. The company also reported breakthroughs in what it called lightweight car body construction and drag reduction, working in tandem with the braking system, treating the entire train as one integrated energy problem rather than a collection of separately optimized parts. When officials at China State Railway Group announced the results, they gave a set of numbers that read almost like a checklist for a system built to disappear into ordinary use rather than announce itself. At 400 kilometers per hour, energy consumption stays below 22 kilowatt hours per kilometer. Interior cabin noise holds around 68 decibels, roughly the volume of an ordinary conversation, and structural fatigue on the load-bearing frame stays within margins comparable to the older CR400 running at its slower top speed. In other words, from inside a CR450 carriage, moving at nearly 400 kilometers per hour is engineered to feel almost exactly like riding the current generation of trains at 350. That last detail is worth sitting with for a moment because it's the opposite of what you'd instinctively expect from a speed record headline. The goal here was never to make the ride feel more dramatic. It was to make an objectively more extreme physical event, more speed, more kinetic energy, more aerodynamic force, feel completely unremarkable to the person sitting in seat 14C with a cup of tea balanced on the tray table. Acceleration tells a similar story, just compressed into a much shorter window of time. The CR450 goes from a standstill to 350 kilometers per hour in 4 minutes and 40 seconds. That's over 100 seconds faster than the current CR400 trains take to reach the exact same speed, the same benchmark speed, reached nearly 2 minutes sooner. On a rail network where trains share track with dozens of other services running tight schedules through some of the busiest stations on Earth, that kind of acceleration margin isn't just a party trick. It changes how quickly a train can merge back into normal traffic patterns after a stop, which has ripple effects across an entire timetable, running thousands of departures a day. None of these numbers exist in a vacuum, either. They've been stress tested against a scale of real-world validation that few transportation projects anywhere attempt. Before the CR450 can carry a single paying passenger, Chinese rail authorities require it to log 600,000 kilometers of operational testing. That's not a lab benchmark. It's the equivalent of driving the full circumference of the Earth roughly 15 times over on actual track, under actual operating conditions, logging how the train behaves through curves, tunnels, temperature swings, and years of accumulated mechanical wear, compressed into an intensive testing window. Some of that testing happened on a closed evaluation loop, the Beijing Railway Test Ring, built specifically for pushing rolling stock pass UT crucially. Much of it also happened on lines the public already rides, the Shanghai-Chongqing-Chengdu corridor, and the Chongqing-Xiamen line, meaning the CR450's headline-grabbing trial runs, including the 453 kilometers per hour top speed and the 896 kilometers per hour passing record, were captured on infrastructure that ordinary commuters use every week, not on some isolated proving ground built purely for spectacle. That October 2025 passing test is worth returning to directly, because it's the moment this story crossed from impressive engineering into something that briefly stopped being about railways at all and started sounding like aviation. The China Academy of Railway Sciences confirmed that 2 CR450 prototypes, moving toward each other on adjacent tracks through the yet-to-open Wuhan-Yichang section of the Chengdu-Shanghai high-speed line, recorded a combined passing speed of 896 kilometers per hour. That figure broke the previous passing speed record, set by an earlier CR450 test in 2023, by 5 kilometers per hour. A small margin, numerically, but confirmation that the platform's performance has been consistent and repeatable across multiple testing campaigns, rather than a single lucky run. For a brief moment, on paper, the relative velocity between two objects each running on ordinary steel wheels touched territory usually reserved for turboprop aircraft. It's worth being precise here about what that number does and doesn't mean, because passing speed and single train speed measure two different things, and headlines have a habit of blurring them together. The 896 kilometers per hour figure is a relative measurement, the combined closing speed of two trains moving toward each other from opposite directions, not the speed either train achieves individually. The actual verified top speed for a single CR450 unit remains 453 kilometers per hour, itself already a world record for conventional wheel-on-rail technology, meaning trains that stay in contact with the track through steel wheels rather than floating above it on magnetic levitation. That distinction matters because it keeps the achievement honest rather than inflated. China does also operate maglev technology, including the Shanghai maglev, which uses magnetic levitation to reach even higher speeds by eliminating wheel-on-rail friction entirely. The CR450 isn't competing in that category. It's the fastest train of its specific type, the type still dominating almost every high-speed rail network on the planet, which is precisely what makes its numbers relevant to how people will actually travel, rather than a demonstration limited to an isolated experimental line. That relevance is really the heart of why this story matters beyond the raw numbers. China's high-speed rail network already spans more than 6 million kilometers of interconnected lines, linking roughly 80% of the country's regions and cities with populations above 500,000. It's the largest network of its kind ever built, assembled largely within the last 2 decades, at a pace and scale that outstrips anything Europe or North America has attempted with high-speed rail. Layering a 400 km per hour service onto infrastructure of that scale doesn't just create one fast route. It compresses travel time across an entire economy. The flagship candidate for the CR450's first major commercial deployment is the Beijing-Shanghai corridor, roughly 1,300 kilometers of track connecting China's political capital to its financial center, currently served by CR400 trains running the trip in a little under 4.5 hours. Shift that same distance onto a 400 kilometer per hour service, and industry estimates suggest the journey could fall to somewhere close to 2.5 hours, edging into territory that starts to genuinely compete with domestic flights once airport transit and security time are factored in. A second deployment is already planned further down the line. Once the second Chengdu-Chongqing high-speed railway, a 292-kilometer route currently under construction, is completed, reporting indicates the CR450 is expected to run there at its full designed operating speed of 400 kilometers per hour, cutting the trip between the two cities to under 50 minutes. For context, that's a drive that currently takes the better part of 3 hours by highway. Now here's where the story needs to slow down and get honest, because everything up to this point has been the momentum side of the CR450's story, and momentum alone doesn't get a train into passenger service. As of the most recent statements from China State Railway Group, the CR450 program is targeting completion of its full operational assessment and final design sign-off sometime in 2026, which is the last formal gate before commercial deployment begins. That is not the same thing as a confirmed passenger launch date, and China State Railway Group has been careful in its public statements not to promise one. Finalizing a train's engineering design in a given year does not automatically mean paying customers or boarding it in that same year. Series production has to scale up after the design is frozen, meaning enough train sets need to be manufactured, inspected, and delivered to actually run a public timetable, not just a handful of test units. Beyond the trains themselves, several candidate routes, including sections of the existing network, may need additional signaling upgrades and track refinements, specifically to support sustained 400 km per hour operation. Since running at a higher ceiling speed safely depends on far more than the train alone. It depends on every signal, junction, and safety system along the entire corridor being certified to match it. Officials covering the project have described a realistic scenario in which full testing wraps in 2026, with commercial service following in a phased rollout rather than a single nationwide switch-on moment. Nobody involved in the program has claimed passengers will be riding at 453 kilometers per hour. That figure will almost certainly never appear on a timetable. It exists specifically as a stress-tested ceiling, proof that the system has margin to spare above the 400 kilometer per hour speed. It's actually being built to deliver day after day for years of scheduled service life. There's also a broader engineering question worth acknowledging honestly, rather than glossing over for the sake of a cleaner story. Wheel-on-rail technology, the category the CR400 belongs to, does have physical limits that don't apply the same way to magnetics. Levitation systems, which eliminate friction between the train and the guideway entirely. Some rail engineers have pointed out that as conventional trains push past 400 and toward 500 kilometers per hour, the physical demands on wheels, rails, and braking systems begin to climb steeply enough that further gains become progressively harder and more expensive to achieve. The CR450 isn't claiming to solve that ceiling permanently. It's demonstrating, with real repeatable trial data, that the ceiling sits meaningfully higher than most of the industry assumed it could reach in daily commercial operation, which is a different, more grounded claim than saying wheel-on-rail speed has no remaining limit at all. So where does that leave the train that supposedly wasn't meant to be this fast? Back where this story started, on that stretch of track outside Wuhan, two prototypes closing on each other at nearly 900 kilometers per hour combined. Neither one built to chase a headline. The 453 kilometers per hour, the 896 kilometers per hour, combined passing speed, the 4 minutes and 40 seconds to reach highway plane velocity from a dead stop, none of that was the assignment. The assignment was quieter and, in its own way, more difficult. Take a proven technology already running at the edge of what most of the world considered practical, and find another 50 kilometers per hour of headroom without asking a single passenger to notice the difference, without extending a single meter of emergency braking distance, without raising the noise in the cabin by a single decibel that matters. The record broke almost as a byproduct of doing that job properly. Sometimes the most extreme engineering achievement isn't the one built to feel extreme at all. It's the one built to feel like nothing happened, running quietly underneath a passenger, doing 400 kilometers an hour. Everything about it holding perfectly, deliberately still. Which part of this story surprised you more? The 453 kilometers per hour a single train in reached, or the fact that engineers built it to feel exactly like the slower trains already running today? Tell me in the comments and stick around, because once the CR450 actually opens for commercial boarding, that's a story worth coming back to see for yourself.